speaker. The speaker is Alexander Wolff. Sasha is a very well-known figure in computational geometry and in graph drawing. Has lots of involvement in various aspects of this as a manager and editor of Journal of Computational Geometry, and involved in a lot of other things, and in the, I guess, in the steering committee of the European Symposium on Algorithms for some years. And the list is way longer than we can afford to read right now, so I will just let him speak. So go ahead, please.
Okay, thanks for the nice introduction, Boris. It was a difficult decision what to talk about, but I thought this is a nice piece of work that's somewhere within graph drawing, but not too far from geometric aspects. So I hope you will enjoy it. If you have any questions, feel free to interrupt me if Boris lets you. I probably will not see it if you raise your hand, so the best is, I guess, if you raise your voice. The first part of the talk is joint work with these gentlemen here from 3 different universities, and the matching or the pointers that point to the affiliation are already a bit part of the first problem or the motivation for my for this work. And I thought it will probably be not, it will not, the talk will not follow the usual way of looking at all the related work first, but we will look at the motivation, and then from the motivation we will jump into the problem, and on the way we'll do all the other things that need to be done. Okay, so what is this about? One of the most cited papers in graph drawing was by these 3 gentlemen from Japan. And generally it's called the Sugiyama framework, which is about drawing layered graphs. So you're given a directed graph as input, and you want a layered drawing of this graph. And this approach that they suggested boiled down the problem, the overall problem, into 5 steps, which are listed here. And the logos should kind of tell you a little bit what is meant by these. But basically, you want to draw a directed graph mostly upwards, and you want it to appear in a nice way. And the last step in this list is the edge routing, and we are interested in routing the edges in an orthogonal way. And the motivation for this comes from technical drawings. For example, such a cable plane, which is used by a company in the north of Germany who they produce tractors and combines and things like that. And if they send a mechanic to a broken engine, then the mechanic needs to understand which parts of the machine are connected to each other. So he looks at such drawings, which are generated automatically. And one small step in this drawing process is when we want to route the edges between such layers. Maybe I go back to the drawing once more. So you see that the dark gray rectangles that they come in layers, and this is part of how this framework works. And now we just look at 2 consecutive layers, a lower layer and an upper layer, and we have some of these rectangles, which are think of them as electronic parts that are connected to each other with cables or wires. And you know exactly which little black rectangles, so-called pods, are connected to each other. And we assume that it's just a matching. Yeah. So now we want to draw these edges in an orthogonal way. And to make things easier, we insist that they all have two vertical pieces and one horizontal piece. So we want to draw the edges like this edge. And we do want to avoid that these edge pieces, these edge segments overlap each other, or that they cross more than necessary. So, for example, this would be an overlap, which we want to avoid. Instead, if we lift this middle horizontal part, then it looks okay. But if we draw that edge in such a way, then we get a double crossing, which we also don't like. So we would be forced to again lift the middle part above. And now the drawing of these three edges fulfills our requirements. And what we want to optimize is kind of the layers, the in-between layers that we need for these middle segments. So we want to use as few of these as possible. Okay, so here's a feasible drawing that routes all the edges in my graph, in my matching. But as you can see, we can improve this a little bit by moving redrawing some of these edges, and then we don't need this lowermost track or intermediate layer anymore. Another thing that we can do to simplify the problem is we can subdivide the edges into two types, namely those that basically go to the left and those that go to the right. And I've drawn them as orange and purple edges here. And yeah, only those that go into the same direction actually cause the problem of maybe intersecting twice. So we have to, they induce some kind of vertical order on these horizontal middle segments. If I would draw the upper orange middle segment below that one, then I would get a double crossing, which I don't want for that reason. So let's a little bit abstract from our graph drawing motivation. And now let's look at intervals. So now my middle segments are nothing but intervals. And I define a directed graph on this set of intervals where I make a vertex for every interval, as usual if you look at interval graphs. But I introduce two types of edges, namely the normal edges. If one interval contains another, for example, A contains B, so they are just connected by an edge. But to express this vertical constraint for my graph drawing problem, I introduce a directed edge from A to C if A is overlapping C and A is on the left of C. Yeah. So from the left interval, I put a directed arc to the right interval in case of overlap. And this will be used to express the thing as a coloring problem. So what I get is a mixed interval graph where I have a vertex for each interval, and for each two intervals that overlap, I either have an undirected or a directed edge. And in my specific case of a directional interval graph, then the question whether I have just an edge or a directed arc depends on the geometry of the intervals, how they are placed with respect to each other. Okay. So in general, for mixed graphs where you have edges and arcs, people have looked at the coloring problem, which means you want to map the vertices of your graph to a set of numbers, such that for every undirected edge, the colors must be unequal. That's the usual coloring constraint. But now we also have directed edges. And for such a directed edge from U to V, we want that the color of U is less than the color of V. And we want, as usually, to use as few colors as possible. Okay. So now here comes the related work section in a small rectangle. So it's known that this coloring problem is NP-hard for bipartite graphs, whereas there are efficient algorithms for trees and for so-called series parallel graphs. Now, for interval graphs, where you don't have edge directions, but just edges, whenever two intervals intersect each other, it's very simple to solve the coloring problem. So if we are given the intervals sorted by left endpoint as down here, what you do is simply the first fit greedy algorithm. So you take the first interval, map it to the smallest color that's available. Then you take the next interval. You cannot color it with 1, so you take 2 instead. Then here comes the third interval. The 1 is available again because the first interval does not overlap or does not intersect the third interval, so you can color it 1. And the last interval cannot be colored with 1 or 2, so you need to use 3. And the reason why this gives you already an optimal coloring with a minimum number of colors is that you can see that there is a clique which is exactly whose size is the same as the number of colors that you have used. And obviously you cannot use fewer colors as that. Okay. On the other hand, if you have a directed graph without any undirected edges, then you can color again in linear time using topological sorting with the same approach. So here's a directed graph that is already topologically sorted for us. And we start again from the left using color 1. Then when we go to the second vertex, we realize, oh, 1 is gone. We cannot use it again because then 2 vertices next to each other, they would get the same color. So we use color 2. The next vertex is not connected to the second vertex, so we can, but is connected to the first vertex, so we can recycle color 2. And then we come to a vertex that has a neighbor that is colored 1 and a neighbor that is colored 2. So we need to use color 3 and so on, basically. You always use the smallest available color. So it's in the idea is the same as for the undirected interval graphs. So these two problems, coloring problems on intervals are easy.
Can I ask a question?
Yes, please.
In the example that you just gave was it seems like you have a directed graph, or this is an undirected graph.
I'm looking.
But this is a traditional coloring, right?
Exactly, exactly. So I'm looking at the traditional extremes. So one extreme is I only have undirected edges, then it's easy. The other case is I have only directed edges, then it's also easy. And
But
now,
what I'm asking is you're not using your directed definition for coloring, right? Because you have a 1 after a 3.
I have one. Yeah. Sorry. Yeah, this is yeah, true. If I would have used, I should have used the definition up here, I guess. That would have made more sense. But indeed, I I confused them. I'm sorry. Yeah,
Thank
good.
you.
So in this case, here, this was wrong, right? The one that should be a 4 if there's a directed edge. You're right. And then this one is also nonsense because it comes from a 2. Indeed.
Thank you.
Yeah. Thanks. These are these last minute changes. Sorry for that. But now here's the case in between these extreme cases. So we have now a directional interval graph, as I will call it. And such graphs we can recognize in quadratic time. We can color them again optimally by a greedy algorithm in n log n time. And then we can use such a minimum coloring, as in this case here. Yeah, this is hopefully correctly colored, this mixed graph, to get my track assignment for the previous problem. So I use the colors of the directional interval graph, and they give me the tracks for my graph drawing problem. There's a one-to-one correspondence. And we also studied the more relaxed model of a mixed interval graph where you're free to choose the direction of the edges. They don't come from geometry. They are not restricted in any, only in that you are only allowed to have an edge or an arc if there is some intersection. And for those, we showed that the coloring problem is actually NP complete. So the restriction to this geometric setting makes the problem indeed simpler. And what I want to show you now in the first half of my talk is the greedy algorithm for coloring. And actually, it's the same algorithm that you have already seen. So we assume that we have an interval representation coming with our graph. Remember, we can recognize these graphs. So even if you don't give me the representation, I can compute one. And the greedy coloring algorithm again sorts the intervals by left endpoint. And whenever it comes to an interval, it assigns the smallest available color, while respecting the incident edges and the arcs, of course. So again, let me show you an example. This set of 7, 8 intervals that are already sorted by left endpoint. And now I want to color them, and the coloring means I will express it by the layers that I'm using here. So the first interval, of course, goes to layer 1 or color 1. The second one intersects A, and that means we have a directed edge. So B must be above A because it overlaps. C also overlaps B. So, and since it's to the right of B, it must be above B. And D now is contained in B and C. But since it's contained, there's just an undirected edge, and I can put it on track 1 or color 1. E is overlapping B and C, so it cannot go on track 1. It must be above B and C, so it goes to color 4. And F again is contained in E, but it overlaps C, so it must go above. And G, it's contained in E, so it can drop down to the first layer, and H can then take the second layer. So It's again first fit, very simple algorithm. The question is, why does it give me the optimum? And here it's not so clear, because if you look at this instance, there's no clique of size 5, for example. So my argument from before, it doesn't work so directly. Okay, but I want to show you this theorem. And the proof sketch goes as follows. Let me define the transitive closure of my graph, which is the graph that you get if you add for each pair of consecutive directed edges a new directed edge. Okay. And now I want to show that actually in that graph, the largest clique the size of the largest clique corresponds to the number of colors that the algorithm uses. And if this is true, then the coloring is optimal. Okay, so let's consider an interval that gets the largest color by my algorithm. Let's suppose M is the number of colors that I use. So I will now again express the color by height. And so this interval V0, it will be on the one of the topmost intervals. And now I will try to construct a clique of size M in this graph G+. Okay, and how do I do that? So I define an interval V2, which is among all the intervals that have a directed edge into V2, the one that has the largest color. So for example, suppose it's here. So it must overlap V0, it must lie a little bit further to the left so that they have this overlap relation that that causes this directed edge from V1 to V0. And then I continue defining a sequence of intervals until I come to an interval that doesn't have any incoming directed edges anymore. Okay, and now notice that by my greedy strategy, the greedy strategy of my algorithm, the colors between two consecutive intervals in this sequence, they are occupied by intervals that need to contain the left endpoint of the upper interval. So for example, between V0 and V1, all the intervals that are in there, they must contain the left endpoint of V0. So here, all these blue intervals that I added now between V0 and V1, they all must contain the left endpoint of V0. Because I went through the intervals from left to right by left endpoint, and by the time I placed V0, this was the only option. So all these colors in between must have been taken by intervals that started before V0. And since V1 is the topmost interval that has an incoming directed arc, these intervals, these blue intervals, must all actually contain V0. Okay? Okay. So this I can use to subdivide this sequence of intervals into stairs or steps, S0, S1, and so on. Each of these groups starts with a red interval, so one of the VIs, and then the blue intervals that lie below one of the VIs and contain it. Okay, so for each of these steps, all intervals contain the upper red interval. Okay, and now I claim that for any steps Si and Sl, every pair of intervals is adjacent in G+. And if I have proven that, then the whole thing is a click, and then I have a good justification why I needed so many colors for coloring them. Yeah. Okay. How are we doing time-wise? Should I go through the proof of the claim?
Well, that's up to you, but you have probably more than half an hour or at least half an hour. So
Yeah. Okay. Then let me jump over this. It's a little technical proof, nothing too special. This is just one slide. And basically, in the end, transitivity gives you the claim. Okay, good. So now I've shown you optimal coloring algorithm. Let me wrap up the first part of my talk. So we have looked at these directional interval graphs. Here up here is again an example for it. Our algorithm runs in n log n time if you implement it carefully. Now this solves the problem for, in my original graph drawing problem, for the edges that go to the left. And of course, you can apply the same algorithm for the edges that go to the right. And in this way, you can solve, you get a two approximation for solving the actual problem of combining the left going and the right going edges in your drawing. So you first solve one of them, put all the middle pieces on the bottom tracks, and then you solve the other direction and put the middle pieces on top of those. That's a two approximation for the number of tracks. And what I have not shown you is a quadratic time algorithm for recognizing such directional interval graphs. And that algorithm is based on PQ trees. And also we showed that if the directions of my edges don't come from this geometric limitation, then the coloring problem actually becomes NP-hard. Now, what are the open problems? And I will look into one in the second part of my talk. So it's only a two approximation. Maybe can we do better than that? We still don't know actually. The running time for the recognition algorithm is quadratic. So can we do better than that? In the meantime, I will not talk about it, but we know that we can do it in linear time. And the other recognition question that we have not solved to date is how to recognize these bidirectional interval graphs. Okay. And one of the reviewers of this paper said, well, how natural is this concept of your directional interval graphs? Wouldn't it be much more natural to have a directed edge for containment rather than for overlap? Okay, interesting question, we thought, and we started working on it after a while. So in this case, for the same set of intervals here, ABC, you now would get a directed edge from A to B because B is contained in A, and you would have just undirected edge for A and C because they just overlap each other. So now this problem has nothing to do with my original graph drawing application, but it's a nice problem in its own right. So this is the topic of the second part, how to color such containment interval graphs. Okay, and let me start with a few observations. So I have not added all the directed and undirected edges between this big set of intervals, but I have added a few on the left-hand side. So you see you get these red directed edges for containment, and you get gray edges, undirected edges, if intervals just overlap. Okay, and I will write for a set of intervals I will write C of I for the containment graph induced by these intervals. All right. Now, let me look at the set of maximal elements in this set of intervals, inclusion-wise maximal intervals. So here I've marked those with a cross. These are the intervals that are not contained by any other interval. And I will use them in my algorithm. Okay. Then the containment graph of these maximal elements is what is called a proper interval graph. And the proper interval graph is simply the interval graph of a set of intervals where no interval contains another interval. That's what makes it proper. Okay. Also, note that if we take the union over these maximal elements, then this is the same as if we take the union over all the intervals. We get the same set of points. Now, really, you consider an interval a set of points, and this is like looking at the projection of these intervals on the x-axis. And it's enough for that. It is enough to look at the maximal points. Maximal intervals. Is the statement clear? The notation you could discuss, but I hope it's clear anyway. And now we look at a subset of the set of maximal elements that is just big enough to also cover all intervals. So in my example up here, I could get rid of this interval up here. It is one of the maximal elements, but if I remove it, I will still cover everything. Yeah. Whereas if I remove this one, there will be a small gap that is not covered. So I better remove this one, and I cannot remove any other one. Okay, now the claim is that the containment graph of this set R is a very simple type of graphs, namely an undirected linear forest. Undirected is clear because no maximal interval contains another maximal interval, so it's only overlaps. And why is it a linear forest? So a collection of paths. Well, simply because it's a proper interval graph. That means it does not contain any induced K13s. In other words, if it was a tree, it cannot branch, and it also cannot contain a larger cycle. And so the only thing that you have to convince yourself that is not excluded already by the fact that it's a proper interval graph is that it cannot contain a triangle. And yeah, it's if you look at three intervals that are all maximal, it's clear that if they would form a triangle like these three here, then one of them can be removed. So it would not be in our set R. That's inclusion-wise minimal. Okay. So since this has a very simple structure, we may as well simply color this one and then kind of repeat with the rest. That's the idea of the algorithm now. It will not be an exact algorithm, but it will be a good approximation. Okay, and here's the result. So it says that this containment graph of a set of intervals can be colored with 2 times the click number of this graph minus 1 many colors. And, the click number is simply the size of the largest click. So that's a lower bound. We definitely need that many colors, but we can do it with 2 times as much as many colors, minus 1. Okay, and how does it work? So as I said, this this subgraph C of R has a very simple structure. It's a linear forest, so we can simply color it 1, 2, 1, 2, 1, 2. That's it. Okay. And if our set of intervals just consists of these intervals in my set R, then we are done. So let's assume that this is not the case. And let's look at the remaining intervals. So the intervals that are not in the set R. Now I claim that the click number of this induced subgraph is bounded by omega minus 1, where omega is the click number of the whole graph. So by removing this linear forest, this set R, from my set of intervals that I need, for which I need 2 colors only, I make the click number of the remaining graph drop by 1. That's what the statement says. So now suppose that there's a click S in G prime, in this reduced graph, that is of size omega. So 1 too much. Yeah, we try to show that there's a contradiction. The Helly property of intervals tells me that if all of them pairwise intersect, then there must be a point in the intersection of all of them. Okay, let P such a point that is contained in all of the intervals in my click. And now, since the set R, as we saw, it kind of covers everything that is covered by all the intervals. So there must be an interval in my set R that contains this point, because it's contained in some other intervals. Okay? And now, if we would add to the set S, which is a click in G prime, the interval R, we would have a click of size omega plus 1. But we have defined omega to be the size of the largest click in G, so there cannot be a click of size omega plus 1 in G. All right. So the claim is true. And then it means we can simply use induction and color G prime with at most 2 times omega of G prime minus 1 colors. So the same thing as I stated in my theorem up here, we now do just for the subgraph G prime. And then we combine this with the coloring of the linear forest R, and then we are done. Okay? So combining these two colorings, the one up here, F1, which just uses 2 colors, and the coloring F2, which uses 2 times omega of G prime minus 1 colors, and omega of G prime we know is omega minus 1. So we will use these together to get a coloring that has the right number of colors. And the idea is very simple. Our final coloring function f uses f1 if an interval is in R, so it will be 1 or 2. And it uses the coloring function f2 that we get inductively, and we simply add 2 to this. So the numbers here, they start with 3 up to whatever was the upper bound. And why does this work? Why does it define a coloring? So we just have to look at 2 cases. If 2 intervals intersect, then obviously the function gives me 2 different numbers because it consists of 2 coloring functions, one for R and one for G prime. And if an interval is contained in another, then I claim that my function even gives me a larger number. And for the first statement, we have to check if x and y are both in R. Well, then it's clear because F1 colors R, so it gives me different colors for overlapping segments. If both are not in R, then I use this lower definition, but this is a coloring of G prime. So if they overlap, they must be different. And then I have also the case that one of the 2 intervals lies in R, so it gets a smaller color, maybe 1 or 2, and the other interval is not in R, so it gets a color that is at least 3. So again, I have shown that this is true. And in the second case, the reason is even simpler. So the contained interval cannot lie in R. So the value of f of x must be at least 3, according to this definition up here. And now suppose that the containing interval would get a larger color. The contained interval would get a larger color, then it means it cannot lie in R. But the F2 value of x is greater than the F2 value of y, and this is the contradiction that I needed. Okay, so using this observation now gives me, it's a constructive proof, so it gives me actually an algorithm for coloring these interval containment graphs. And if you implement it carefully, you can do it such that it runs in n log n time. Okay, and the reason why it is a 2 approximation is simply it uses no more than 2 times the click number of the graph. Okay. Now, how good is the algorithm? Here I will give you a family of intervals that shows that there are examples of sets of intervals where the click number and the coloring number are exactly as far as apart as the number of colors that my algorithm uses is away from the click number. So in the limit, this gives me a family of intervals where the ratio between the chromatic number, the number of colors, and the click number, so the size of the largest click, they are a factor of 2 apart. And the family looks like this. I have 2 intervals that just overlap a little bit. Now, the colors are not the colors. The colors are actually the heights. And now I recursively put 2 similar intervals into the first and 2 similar guys into the second. And now I do the same for the 4 green intervals. And to make the numbers work out, I use one more layer where I put a purple interval into each of the red ones. And yeah, you can see that in this case, the largest click is of size 4, I guess. So here you take 1 of each color. This gives you a size of 4. But the number of colors that you actually need, you can see here is by this thing here, it's 7. You cannot do with fewer. I mean, you could move down a few of the intervals, but you would, for this rightmost little interval, you would still be forced to place it on level 7. So this shows you that if you continue this construction, then you reach a ratio of 2. Okay. So it means that no algorithm that is based on the click number can really be better than our algorithm. Okay, and we also managed to show that the problem is NP-hard. Okay, so yeah, it's NP-hard to decide whether the chromatic number of this containment interval graph is bounded by a given integer k. And our reduction is from exact 3-sat, meaning that every clause has exactly 3 literals. And I will mainly prove by picture. Don't worry. But of course, we are given these clauses, and we use variables x1 to xn, and then there's a number. This h will play the role of k here. And how do my variable gadgets look like? We called those Christmas trees, which comes at the right time. They look like this. There are a lot of intervals contained in each other in red and in gray. They have a little extension on the top. Don't ask me why we need it. And then there are some long sequences of blue intervals that go to the right. We will see in a moment why we need them, but let me switch between true and false so that you see what the 2 values of the variables mean. You see? They go up and down and kind of change order. And when the red one goes up, it also forces these blue guys to go up. So if I go up, then these blue guys also go up to 5i plus 3, whatever I is. Okay, and how do I use these things? Now we construct one of these Christmas tree for every two of these for every variable, but then also we will have some for each clauses, and the overall image looks like this. I have a red and a gray Christmas tree for each variable, and then I have these blue long intervals that are actually subdivided if you looked carefully in the previous picture. And they line up, three of them line up with each clause. And now let me change the value of x2, I think, no, x4. And this will increase the height or will push the middle blue Christmas tree up. And that means that it will actually use one color more if the three-set formula is not satisfiable. That's the idea of the clause, of the construction. So this graph induced by this set of intervals admits a coloring with this h number of colors if and only if my Boolean formula is satisfiable. Okay. And since we had this nice construction, we also extended it to bidirectional intervals, where for each interval you're now given a direction, left or right, and you get a directed edge in the intersection graph if they both go left and one is further left than the other, or they both go right and they overlap, and the edge will go from the left to the more right interval. And the statement is the same. It's NP-hard. Okay, and the construction, I will not go into details, but it looks very similar. You still have these gray and red parts that make a variable. You can move them up and down. I will do this here so that you can see what happens. And there are also clause gadgets. And if your clause is not satisfied, then it needs an extra track and therefore an extra color. And yeah, this is the decision problem. We don't know, we were not able to modify our constructions such that the gap is larger, so that if the formula is not satisfiable, that you need a lot more colors. So in order to show some non-approximability result, we didn't manage to. Okay. Now it's getting very late. I had one more algorithm for mixed interval graphs. So the more general case where the direction comes not from geometry. But since you are geometers, I suggest we skip this part, and I will jump directly to the last slide, and I'm ready to take questions, I guess. So this was the proof, and this was the example for this mixed interval case. And this is an overview of the results we have. So we got for containment, directional and bidirectional and general mixed interval graphs. We have shown that most of these cases are actually NP-hard to color, except for the simple directional case. I showed you this algorithm. I showed you for containment graphs the bound 2 omega minus 1, which gives us a 2 approximation. And I have not talked about recognition at all. And I just skipped this general mixed interval graphs. Yeah. Okay, and regarding recognition, we have some follow-up work that's still not published yet, but in the pipeline. So we showed that if you don't just give us a mixed graph to test whether it has whether it is a bidirectional interval graph, but you also give us the orientation of the intervals, so whether they look left or look right. If you add this information, then we can solve the problem in linear time. And if you orient all of them, say, in one direction, say to the right, then we are in this directional interval case. And so we actually improved upon this quadratic time recognition by solving a more general problem. And that's the end of my talk. Thanks for your patience.